All right. Well, thank you for joining us and welcome to the June edition of the Pigment 101 webinar. We're happy to have you and we will go ahead and get started. So I am recording this webinar, so all of those in attendance today will receive the link to the recording as well as the PDF of the presentation. As always, if you have any questions along the way, feel free to enter them in the chat box and I'll address them at the end. So we'll go ahead and get started. So today we are going to talk about dispersion endpoint and the impacts that both formulation and pigment does have on that endpoint. And of course, how do we get there as far as test methods and what's appropriate and what's not in there. So big category, big topic. So hopefully I can provide you a little bit more insight into this particular topic area. So there's a number of ways that dispersion endpoint can be impacted in here. So of course, before you can assess the impact of pigment and formulation, you also have to have a reasonable way to assess, am I at the endpoint? So one of the biggest used tests out there is the Hegman grind in there. So I kind of say that this particular test method is one of those ones that have a love-hate relationship with it. So in reality, I wanted to be able to provide with a little bit of insight on what it is and isn't, where it can be used and where it shouldn't be used, as well as other methods and potentially a best method or a best combination of methods for that dispersion endpoint assessment. Now, once you have a good understanding of how to assess your endpoint, then you can ask the questions of how does formulation and process impact that endpoint as far as dispersion selections, the pigment particle size and shape, the actual pigment itself, and what kind of finishing techniques were used for that particular one. All of those will go into understanding how the endpoint is impacted by those types of things once you have established a reasonable methodology for assessing the endpoint. So the Hegman grind, again, it's a useful tool, but it's limited as to what it can tell you. It is not the correct tool if you're trying to understand how well your pigment is dispersed, both from color and a strength dispersion standpoint. So it's not going to tell you that. Primarily because the Hegman dispensers very coarse particle size, visual particles that you can see with your eyes, which are not usually the particles that dictate whether you're at the endpoint. As I mentioned, it only detects very large agglomerates, so it's a good tool for that very early stage where you're still in a very coarse dispersion. Again, it's a visible thing. So if you can see it with your eyes, then it doesn't necessarily tell you that you've optimized your dispersion formula or your dispersion process. Color development and strength always happens at the submicron level in there. So you can have good Hegman readings while still having a lot of room to move in your dispersion development in here. So what I don't want to leave you with is that this is the test that's going to tell me whether I'm done or not with respect to my dispersion in there, because you can have very different similar readings and very different endpoints for dispersions. This is not something I'm not telling you that's anything that's new, but for those who might not be as familiar with it, it's a very visual, hands-on test where we look for the visible particles and where they fall on a graded plate in terms of size in here. So it's a quick and easy test. Yes, I will agree with you on that one. However, it's not very sensitive enough to use as a dispersion endpoint test method. It of course doesn't measure the strength, and strength, as we know, is depends completely on how well those agglomerates that come in from the bag of pigment, how well they are broken down and wetted. It Hegman does not correlate well with the optical performance in there, so you can easily pass that Hegman grind spec, but still be very underdeveloped in terms of strength or color development, or transparency, whatever the end property is that you're trying to achieve. It doesn't reflect any kind of color development in terms of did I develop the most out of my pigment during my dispersion in here. So it doesn't give any insights into those in there. So the certainly not a color tool to be able to assess your dispersion. It as I mentioned, it's not good for the endpoint. It can be used as a quick tool at the very early stages of dispersion, because what we see with this particular that the Hegman values do improve very quickly through those early stages. Again, it's the visual ones that you see with your eye, so they're big particles. In that mid stage range, you'll see that the Hegman will plateau and won't change anything. Meanwhile, the strength, color, transparency, whatever you're looking for, will still continue to improve. What I want to get across it here is that I don't want you to be in that false sense of we're done when your dispersion's not fully done in here. And I have a visual to help you with that area. The other thing is operator variability. Because it is a visual one, it's subjective to the person doing the testing. So it depends on the light, the experience of the person doing the testing, and the drawdown technique that is used in here. So a lot of different outside or external impacts can make the result itself somewhat variable. So this is the visual I was talking about to show you that the Hegman is good early on, but it does plateau fairly quickly, while your other methods and I'll say that your more important methods of assessment are still continuing to improve along the way. So that false sense of endpoint can lead you in a wrong position in here, so that you might pull the dispersion too early. You haven't received all of your benefits of that dispersion. Bottom line, as I mentioned many times, it's good for course quality control. I've never saw it as a performance metric, and that's key. When you're making dispersions and you're trying to get the optimized performance out of that dispersion, you want a metric that is specifically related to that performance. So it's great for seeds or contamination. In my previous life, it was always good for detecting if my media passed any, or if my mill passed any media, and the media was getting a little bit chopped up in there. I'm thinking like glass beads in the sand mill type of thing. If some of those pass and get ground up, that's a great tool for seeing those, because they are very visible to the eye, so that we can do that. Not reliable, like I said, for development of color development or strength development in there. It's also not a good tool to use if you're trying to optimize your dispersion process. in terms of energy and time for that aspect of it. So it has its place, just not as a standalone endpoint tool. Of course, now you're going to ask what is the best endpoint methodology to use in here, and you know, the proverbial "it depends" applies here, depending on whether it's a transparent or an opaque. They have different needs and techniques that are best suited for them. But typically, it's a more of a combination of methods to be able to assess that endpoint. Transparent pigments are behaved very differently from opaque ones. So the signals that we are looking for in each of these are not going to be identical. So a good time to understand those differences, of course, for the primary driver for a transparent pigment, of course, obviously the chroma. We want to develop the most chroma that we can. Clarity or transparency, haze, whatever terminology you want to use, that's important in transparency pigments because those are always going to be, a lot of times they're going to be used with effect pigments. So you want to be able to have a good transparent dispersion so that the effect pigments that you're using stand out like you want them to do. On the contrary, for opaque pigments, those pigments do need to be able to scatter as much light because you want them to be opaque. In that case, tint strength is a very good methodology to use for that one. From a testing perspective, mass tone color for transparency, and I'll add on to that one, haze or transparency is a good way of tooling. You can get get both of them with one drawdown. Tint strength for the opaque pigments. From a color sensitivity, very high for transparent, moderate for opaques, and then go on down. And you'll see in both cases the end stage of the dispersion, the Hegman value will be sort of non-existent because you won't be able to see those differences on that methodology. Again, as I mentioned, it's a combination. So early on, you might just use that quick and easy Hegman in the early stages. But then you need to bring on that primary metric that you've assessed for that particular pigment to be able to follow that development. Along with those, there's a lot of color data that you can get. And then you could also add in more system-specific types of tests, where, for example, rub-ups for a water-based system might be an added tool that you want to add into your matrix. But the bottom line is for transparency, transparent pigments, we are we maximizing the color quality? And for opaque pigments, are we maximizing the efficiency and hiding aspects of it? So a little bit more detail for each of these types of pigments. On the transparent side, as I mentioned, mass tone, we don't think of mass tone with respect to a transparent pigment because of course, they don't hide, but there's other ways of getting that color information in there. And typically these are done by drawing down on a mylar or a plastic sheet to be able to measure that color over using a black and white card or whatever your procedure might be. But that's a measure to be able to understand how that color is developing. In there. So as the dispersion goes on, you're going to see how that chroma increases, how the hue shifts towards the direction it's supposed to go. And then at some point in time, it will be stabilized, and that's usually your endpoint in there. And so L star typically will decrease as it improves, which suggests that the particle size is decreasing as well. in here. So that is kind of there. And ultimately, as the picture shows, is we want to be able to create those nice, stable, and separate particles in the dispersion. From a colorimetric perspective, a lot of information you can get from that very simple drawdown, where you can track that delta E performance from one test time to the next test time. You can track the color as well. You can do it against itself to show the tracking over time. And as well as if you have a standard, you can be able to understand where you are versus a standard that you've set up. And the endpoint really is your discretion, but it's really that that the delta E doesn't change very much within the intervals that you're looking at. I just suggest something on the order of 0.2 or 0.3 or less, because it will plateau over there. And of course, the A and the B also stop shifting and are more stabilized in there. Of course, you could always continue to grind, but your input energy and your resulting increase start to change directions, where you continue to enter input energy to the system, but you're not going to gain anything significant to be able to do that. So that's just something that with your formulation, your process, and your testing perspectives have to develop that. This is an example of a pigment blue 15-2 in here, and this was a set of work that we did to take a look at dispersion, the dispersion chemistry's impact on color development. 15-2s are the alpha blues. They are the red shade blues. So ultimately, we want to be able to develop the most red shade in terms of its color, as well as increasing that blue space that it is done. So in this chart, we want to go in that down left-hand arrow in terms of color development in there. In this case, we can see how that formulation really plays a role into how well the dispersion gets developed, how well the color gets developed, and whether or not we can get more out of our pigment by formulation. Given everything else being the same, in this case, the knob that I'm showing here is the dispersion selection. Strength and it can still be used for transparent pigments, but it's a little bit lesser from a sensitivity perspective than the full tone mass tone color, and we start to see a little bit lesser of a change in terms of time period to time period with respect to color shifts. My favorite is transparency or haze, depending on how you're doing it. They're transparent pigments, so we want to understand where are we, and are we at the plateau from a haze or transparency perspective. This goes in combination with that the mass tone measurement. We can get combine both the mass tone and transparency or haze with one drawdown. So we can get a lot of information with a very simple drawdown to be able to understand, are we at the endpoint? This is, again, the same example of that 15-2 blue from a strength perspective. So strength is important. Obviously, we want to get the most out of our pigment. And so this just shows that, again, like color, formulation really impacts how much strength that you can develop in a given formulation based on the dispersion that you choose. So I'm not selling Hunter lab equipment as a side job, but in my previous life, this is something that I was always a big fan of, this type of technology that helps us to understand, to both measure color, measure haze, or transparency, depending on if you're using a standard in here. So it's a great tool. and can take that visual into a numeric assessment. Again, that visual on your left-hand side, that visual that I have here shows two different transparency positions of a dispersion, so that you can see on the left-hand side something that was a little earlier in the process, but left in the mill longer. We develop more transparency, so the visual is clearer on the right-hand side. How does that translate into numeric information? That this is what you see here on the right-hand side, where we're looking at two different drying processes for the same type of pigment, and we're seeing that in the gray line, the particular product starts with a low haze, but really doesn't improve any more over time in here. So in this case, it's already plateaued early on, whereas the other drying process starts at a higher level and takes some time and really doesn't get to the same level. So it would need some increasing of time for that aspect of it. A simple way to do it, you don't even need an instrument to do this. You can do that with your drawdown and over black and white, and measure the contrast ratio. So just like we do for opacity, we can do the reverse for transparency. So in this case, a lower contrast ratio indicates a better transparency. So these are the same Pigment Blue 15 2 samples that I've been talking about in different areas, and we can definitely see how that dispersion selection for this particular pigment makes a big difference in transparency as well. So what not to rely on? Obviously, we're not going to rely on Hegman for the entire process in here. Early on, it is good. Strength alone certainly can misunderstand it. So I like to indicate that that the transparency endpoint, you can get a lot of data from one drawdown, so that you can be very efficient in your testing, as well as be more confident in that endpoint, that you are at the endpoint, the hue stabilized, the delta E stabilized, your transparency or haze has stabilized. That tells you that you are at the endpoint for that particular dispersion batch. Opaque. Mentioned that obviously the idea here is to have that opacity, that hiding power. So that's our goal, is to maximize that power, but yet also get to a stabilized dispersion as well. Strength is always good for that one. The key here is for your testing system that uses a TiO2 system, that really does have to be a very controlled standard testing base to be able to do that. If there's a lot of variability in that testing base, then it will also introduce that same variability into your test, as well as that tight ratio control when you're doing that testing. So weighing accuracy and a good, tightly controlled standard testing base is key when assessing strength. Essentially, what we're looking for is when that strength reaches a plateau in there. The key here is, because opaque pigments depend on light scattering, we want to be able to get to that particle size that we're looking for the most high, but also we need to develop the strength and color to be able to do that. Other ones that you can use in the same time, like on the transparent side, you can also track delta E and the A and the B values as time goes on, to be able to find where they maximize. Um, the key here is because we're looking at strength as being the main driver for opaque pigments, when that does plateau, the mass tone color can still shift. And these are especially critical for those softer organics and some inorganic pigments, especially in that yellow, orange, and red pigment color spaces. They tend to be on the organic side, they tend to be very, very soft. And so milling them more, one is not going to get you any more strength out of it, but it's also going to shift your color. Excuse me. So you may have heard the term that we're burning the pigment in there, and that's what you're just grinding to a different mass tone location to be able to do that. So that's why following strength is a key on that area. Um, just like on the transparent here, you can also look at the contrast ratio to make sure that you are optimized there as well. Again, when there's no further improvement, that signifies that you are done. So these are easy tests to do for quick tests, but they also don't necessarily, or they will give you that endpoint, unlike where the Hegman is at the very beginning. Of course, you can always add on other tests that might be critical for that particular system. I mentioned the robot test for water-based systems. That's another approach to make sure that the dispersion is stable. Same here, Hegman alone not only ensures no seeds or contamination, and especially on these softer ones that you typically go into a sand mill or a glass media mill. We don't want any glass to be in the dispersion itself. So again, a simple testing can be done with one drawdown. You can get a lot of information from that one drawdown. So now that we understand how to measure that endpoint, then it's important to understand how the factors influence that endpoint. So we've seen this one before, that pigments are developed for applications area. So they're put together in very specific approaches so that they can be optimized in that end application area. It's not to say that they can't be used in other areas, but the important part to understand is that they are unique in the product themselves, but they just happen to fall under a color index. So there's many products available in that color index. They're going to have a shape. When the pigments are synthesized, they create a shape based on that chemistry. And that shape dictates a number of things. It's going to dictate how much surface area is there and how much dispersion is required. It's also going to dictate how big the agglomerates are that are created. Now, remember, the agglomerates are, here we go. The primary particle size is achieved only once when that crystal is formed. Once it forms, it then comes together with other primary particles to create that aggregate. The aggregates are extremely tightly bound. They're not going to come apart in there, and that's essentially, when you're talking about a dispersion endpoint, that is the goal that we want to reach. We want to get down to that aggregate stage. So you'll never get to the primary particle size. Then those aggregates come together in the agglomerates. Those are loosely bound. That's really what you get in the bag when you're trying to do that. So as they become the looser they're bound, the easier they are to wet out and disperse, of course, in there. So That's what we're trying to do. The pigment out of the bag are these big agglomerates that we want to go through that process. We need to wet them. And then once they've been fully wet, so your premix process is extremely important because we wanted to put the time and energy ahead of the mill itself so that we can utilize the mill to the best efficiency as possible. So even though it's just putting together the all the pigment and the solvents and the resins in there, that process is extremely important so that we wet the pigment as best as possible before introducing it to the grinding stage. Once it's ground, of course, you put all that energy and time into separating them all. We got to make sure that they are fully stabilized, and that's where your dispersion selection is very important to be able to do that, because you don't want them to come back together in a flocculated state. Then you've just wasted all of that energy and investment in the grinding stage to be lost because it's not stable. Again, another visual to help in there to understand when it's a fully dispersed, there's going to be these individual particles, which are the agglomerates. They're well coated and wetted out. They are staying away from each other, either electrostatically or steric stabilization. Depends on what dispersant that you're using in that particular formulation. But the key here is we don't want any flocculation to occur and those particles to agglomerate back together again. If we get to that stage, we are going to achieve the maximum color strength and hiding that we can achieve with that particular pigment. Other properties that come along with that as well. But ultimately, this is where we want to be with our dispersion. The opposite is true if it is turns out to be a flocculated dispersion. So you spent all that investment and time and energy going through the mill, but if the dispersant isn't chosen properly or it got shocked out somehow, then all of a sudden these particles that you've painstakingly separated now come back together again, and you see these very large particles in there. They start to settle out, they become unstable, and then it's a poor dispersion that you can't use. It has to be reworked, and that costs additional time and money to be able to do that. So I talked about the particle shape that leads to the agglomerate or aggregate particles as well, and then that leads to the surface area for each of these pigments. What this table really just shows is these are all pigment yellow 83 pigments, just of different particle sizes, opaque to transparent. Those particle sizes result in obviously different surface areas, and then that's going to necessitate a different amount of dispersion level to use to make that dispersion stable. Again, we want to grind them, but we also need to stabilize them in the system. Dispersions themselves, they come in all flavors and shapes and sizes and technology in here. So all the way to the basic polymer that has one terminal group that likes the pigment surface, and the tail goes out into the vehicle matrix, all the way to the most high-tech cone copolymer. As you can see, there's many of those pigment-loving groups that attach to the surface of the pigment, and the tails themselves go out into the vehicle matrix to be able to further stabilize those. So everything and everything in between there as well. We did some work. I shared with you some data pages from this work earlier in the presentation, but this gives a feel for how we looked at the dispersant structure in here. Our intent here was to evaluate these types of technologies in terms of um, of the polymer itself and how well it does on dispersing this particular pigment. So they all have the same formulation, just the polymer itself is different. And we also took a look at synergist. The phthalates some phthalates tend to like an additional synergist in there. So we looked at these with and without synergist as well. So going back to that original dispersant slide, I put in the types of dispersants that we looked at, block copolymer, a random one, and a comb polymer in there. So obviously, when we're looking at some of these variables, you saw the earlier charts of strength and transparency and color development. Viscosity is another tool that we've used to evaluate the impact of that dispersant in here. So you can see that data here. And then if you're looking at sort of a toolbox for your formulation, it's always good to say, all right, well, I did my evaluations on these, and can I apply that to the other phthalates, blues and greens in my system that I want to have? So what I'm showing here is that comparison to the sort of the best of the best for the pigment of choice, the 15-2 of choice that we used in that experimental design. And then we started applying it to other phthalates. So we're going from an alpha to an alpha, but a non-flocculating blue 15-2 to a standard 15-1 in here. And we start to see some differences between the responses for that. They're still both alpha ones, but the surface treatments that are used interact differently for these. Oops. Yeah. So next we go from we switch over to the beta, the 15-3s. Here we see a marked difference between two of the three good choices that we liked for the 15-2 and one that was very good for that one. And then going from the alpha to the beta, both non-flocculating, again, different differences in. And then, of course, the blue to the green in phthalo space, we see those changes as well. What this allows us to do is to select a toolbox where you can have, in this particular case, a desired dispersant polymer, and then an option to use or not use a synergist, depending on the performance area. So your toolbox is as small as possible, but you gain the most impact. So you've seen this chart before many times. The pigment chemistry typically results in about 75% of the performance, but how we finish it really shifts in one direction or another. And you're going to see definitely how the three areas interact with each other in terms of performance, overall performance. Finishing, of course, we talked about this in earlier webinars. It matters because it's a way to link the process to the performance in here. So selecting the right product is just as important as the formulation and process as well. Because ultimately, you need to maximize all of your performance areas, your strength, your transparency or opacity, and then stability. So you've seen this one before where there is both chemical and mechanical in terms of the techniques that are available to our development chemists when they put together a new product. Those differences, you can start to see them on TDS type data in some of these areas to show that that there is a difference in the finishing technique used to be able to generate different physical properties of the pigment. An example, another 15.2 here where we took a look at the impact of drying on the color development as well as the strength. And in this case, it's an alpha blue, so we still want to develop the most redness that we can, as well as the most blueness we can. And in this case, we start to see the drying process number 2 as giving us the most color development as well as the most strength in there. So in this particular formulation, the combination of the finishing as well as that formulation, we see a difference between the drying process. From another aspect of it is strength, just as we talked about there. Here, when we look at in a powder coating formulation, 3 different Pigment Blue 15.3s, one that was created for plastics, one created for a coatings application, and one created for ink. Those finishing choices result in a difference in the strength that we could develop in this particular formulation. Physical performance area, we start to see, so even though in the previous chart, the coatings and the plastics grades were very, very similar in terms of strength development, in a impact resistance in the same powder coating formulation, we see a fall off of performance in the reversed impact of that coating grade in there. So yeah, all properties need to be put into a balance to be able to choose the best product for your application. My favorite chart, but it remains to be true. It's going to be balanced to be able to choose your pigment, choose your formulation, choose your process. All that ultimately leads you to selecting the best test method or methods to be able to get to that end dispersion point, so that you've gotten the best for your money invested into that dispersion. And that's what I have for today.